Good morning, everyone. Thank you for the audience, and it's a pleasure to be here to announce the USP lecture of today. USP lectures are an initiative from our Research and Innovation Rectory, and I'd like to thank you, the Rectory, on behalf of Professor Paulo Nussensweig for such opportunity. And I'm happy to announce today Professor Jan Rabaey from UC Berkeley on his talk today of brains and computers. Professor Jan Rabaey is an emeritus professor of the Donald O. Pedersen Distinguished Professor at the Electrical Engineering and Computer Sciences Department at the University of California, Berkeley. Professor Jan Rabaey research had a strong impact in the semiconductor industry in the past 4 years, and amongst his many positions, he's also the Chief Technology Officer at the Systems Technology Co-Optimization Division at imec, one of the biggest semiconductor centers, maybe the biggest in Europe, as well as in the world. imec is located in Belgium. Professor Jan Rabaey also is a long-term collaboration of Brazil, advising many students and helping us a lot developing the local semiconductor industry. As an enthusiast of technology, I think we'll have a very exciting lecture today. Thank you, Jan.
Well, good morning. Thank you, Marcelo, for the well welcome. And it's a true pleasure for me to be back here in São Paulo. I think it's about my 4th visit or something like that. And it's always a pleasure. So the lecture I'm going to give today is kind of a combination of experiences I had. About 15 years ago, I started working on the domain of brain-machine interfaces, being capable of connecting the human brain to the electronic world, basically to help address some neurodegenerative diseases, particular situations where people basically get harmed because of the fact that part of their neural system is not functional anymore. But that brought me in contact with a very broad range of people from both neurosurgery, neuroscience, and computational neuroscience. And it has helped me to get some insights in the differences between biological computing and physical computing. And that's what we're going to be talking about today. What are the differences between those two worlds and how they can learn from each other and why they should learn from each other. So it should be as no surprise that computing, the demand for computing is enormous and is growing exponentially. And this is true at every single domain. You think about cloud computing, the giant data centers that are popping up all over the world. We have our mobile devices, which I call the edge of the network, which we all use today to access information, to basically deal with information, enter information, communicate, and so on and so forth. And more now we have the third circle, which is now primarily called the Internet of Things, but has many other names like the Industrial Internet, the Internet of Everything, or what I call the swarm. Numerous devices around us that connect the world, the physical world around us, with the cyber world. Now, all of those basically combine computing, and again, the demand is growing. This is an interesting chart. It is a chart that shows the world compute performance in zillions of operations per second. Now, we're not used to those numbers, zillions. What does a zillion mean? Well, one zip is actually 10 to the 21st instructions per second. Or if you want to basically look at it, this is about 100,000 of the best supercomputers today. That's what we're basically consuming in terms of computing. And as you can see on this log curve, it is exponentially increasing. So if nothing happens, this will be the trend forward. And by the year 2040, we'll be sitting at about 100,000 zips of computational requirement. This ain't going to happen. And there's a couple of reasons for this. Actually, it is more likely that we will see a flattening out at around 1,000 zips or zillions operations per second by the year 2040 and 50. And there is only one good reason for this. The reason is energy. Computation takes energy. And as you can see, the amount of energy that's being consumed in joules per year, again, is also going up exponentially. Now, that cannot go on, because if you extrapolate this, computing would take more energy than the whole world energy production by the year 2040 or something like that. So by nature, it's going to be limited by some amount of power consumption. Now, does that mean that computing is going to slow down or halt? Probably not, because we are smart. We might make computing more energy efficient. That's really the only solution to it, is how can we make an operation more effective. Now, in the past, we've been very good at this. We basically had something which is called Moore's law and Denard's law, which basically allowed us to make transistors smaller and smaller continuously. And with that came some other benefits. The transistors became faster, and they became more energy efficient. So that was an interesting thing we had going for us. Basically, computing became cheaper by basically adopting new technologies. Again, this is slowing down. Actually, since about 1990, the reduction in energy per operation has been slowing down. And asymptotically should go to something which is called KT, as the Boltzmann constant times the absolute temperature. Below that, it's very hard to do digital, basically digital operation basically does not make sense anymore. It's basically noise. So we see that we're going to level out on that perspective. And so if that doesn't help anymore, what else can? What else can we do to make our computations or our computers more effective? And a lot of people thinking about this, obviously. This is a really important topic for society. So what are the options? Well, we might come up with newer transistors. And there's indeed some very clever devices, architectures, and materials that are being used. Like, for instance, 2D materials as an example. Optical computing, using light. Quantum computing obviously plays a role as well. Organic computing, computing with molecules, is maybe not fast, but is very efficient. And the last one, that's the one I'm going to be talking about today, is look at our brain. See what we can learn from nature and how nature does computing, and potentially basically adopt some of those concepts. So let us get us some background on nature, on our brain. Our brain is an amazing computational engine. It has the most amazing thing that basically struck my mind right away is that it basically performs all its functions, this very complex task we do every day, at about 20 watts of power dissipation. That's a small light bulb. That's all the energy it takes to make our brain basically operate. And with that 20 watts, it performs about 10 to the 16 floating point operation per second. Now, that's an estimation. Nobody really knows. So this can be wrong by an order of magnitude in both directions, but don't worry too much about that. The bottom level, however, is per operation, it's about 2 to 3 orders of magnitude more efficient than today's silicon components. It has some other interesting features. It is those devices, if you look at your brain, we basically lose neurons on a day-by-day basis. They basically die off, some accidents happen, things like that. Even that, if that is happening, we don't crash. We are very robust. The brain is a very robust engine, and the failure of some parts doesn't mean that the whole machine goes down. It also has a lot of variations. Not every single neuron is different in terms of size, length, and so on and so forth. So huge variability. And then the last one, which is very important as well, is that we can do amazing things with devices, neurons, that are actually quite mediocre. They're not fast. A neuron is a very slow device. It has high variability. The time resolution is small. Yet we can do tasks like vision, an amazing task of looking at objects, the world around us, interpreting it, and basically make sense of it in an accurate way. We can hear sounds and find directionality between sounds, which is basically quite amazing, given the fact that the sensors we're using are actually quite slow, slower actually almost than the time differences that we can observe. So some very interesting properties, and I think it's worthwhile to learn from that and see if we can bring some of those ideas to the physical compute world. Now, it's not easy. I'm quoting from one of my friends, a colleague in Berkeley, Bruno Alshausen, who is a computational neuroscientist. He says, biology is hiding its secrets well. We just don't have the tools yet to grasp the complexity which is going on. And that's entirely true. If you look at the brain, many pieces we don't understand. Definitely, if you go to the higher abstraction levels, we have very, very little inkling of exactly what's going on. But at the same time, science, technology has brought us a number of tools. fMRI, implant devices, neural probes, and so on and so forth, that now allow us to peek into the brain and see what is going on. And hopefully with that, we're going to get better understanding of the basic nature of what basic cognitive computing is all about. So that's kind of the setting for this presentation. I think there's an opportunity here. And let's figure out what that opportunity is. But before we go there, it's probably worthwhile to look back a little bit. Look at some history. Computing, physical computing, and organic computing are basically born along very different paths, and they've evolved along very different paths. So they have different histories. Computers have been there for a while. Even the Egyptians already used abacus to do some computation. But it was really in the early 1800s that people started to build mechanical machines to do computing. For instance, the Babbage computer, which is very well known, very complex mechanical computing. But it turned to be extremely expensive on one side, and number two, not very reliable. So mechanical computing quickly got replaced by more electrical or electronic components later on. The invention of the vacuum tube allowed us to do some logic gates and the first layers of computing, leading to the ENIAC computer in 1940. So then think about it. This is only about 80 years ago. It's not a huge amount of time. And then obviously things got into an acceleration mode because we had invented the transistor, the integrated circuit, and the rest is really history. What has happened is that computers that used to fill up rooms became things you could have boxes in somewhere in a corner, on your desk, in your hands, on your body. So we have basically scaled down computing in size substantially over that period of time. The other thing which is very important and has also driven computing substantially is that those devices were not isolated. They were connected. Networks started to emerge. Especially in the 1970s, the introduction of the internet, or the DARPANET as it was called at that point in time, was the first step to bring computers together and do tasks together. The World Wide Web came 1990s, and nowadays we're talking about cloud computing, massive number of computers in rooms working together to do complex tasks, and we're now moving to the world of swarms or IoT, of millions or trillions of devices interacting. Now, so the evolution really is that computing has gotten smaller and smaller and smaller. If you compare the sizes, we see we have an exponential decrease in volume or the density of computing has increased substantially. And the main reason, as I already mentioned, was that transistors were getting smaller. Moore's law basically said, still happening, will still happen for the next 10 years. No question about that. We still will see transistors getting smaller to about 1 nanometers in about 2032 approximately. Okay? So this is the computer evolution. Now let's look at the biological side. Now the brain has gone to some much longer evolution. Right? So the first cells appeared about 2 billion years ago, and then gradually things became more complex. It's about 2 billion years ago that some cells started using electrical signals to basically send information across the cells and basically do things together. And gradually but surely this really translated into the first form of a neural net. Especially in things like worms and things like that. There were a class of worms that have a very primitive network, maybe 200 neurons, that help them to basically move forward and find food and so on and so forth. But then things became more complex. More and more competition happened, so you had to be smarter, you had to put more functions together, and it's about, again, about 500 million years ago that we saw the first kind of more centralized computing happening, which is the emergence of the primitive brain. And then it went quickly. About 200 million years ago, we had the rodents started forming a fairly already had a complex brain involved, and hominids and things like that appeared about 200,000 years ago. Now, the difference, so we have seen in evolution, and it's still evolving. The difference with what happened in the computing is that there was no form of networking per se. We cannot connect brains together into a single network. But we had another means. We had communication. Really important. Society got formed when people started to communicate, interact with each other, doing things together. So our form of networking was basically through vision and sound, voice, gestures, and so on and so forth. And that's going to be important because that's going to come back later on. Now, computers got smaller, brains got bigger. If you think about, again, for the last couple of million years, you see that the brain of the hominids basically has gone up very rapidly. Especially in the last 100,000s of years, you saw very rapid growth in the brain. Now, there's one little kind of interesting tidbit you should know. That kept on going till about 10,000 years ago. And then suddenly, brains started to get smaller again. Actually, our brain of today is smaller than our ancestors of 10,000 years ago. And there's many discussions why this is. But I think one good one, and again, is going to be important later on, is the fact that as we started to go into societies, living into cities, agricultural communities, the idea that everybody had to know everything disappeared. We had specialization. You had people that became farmers, plumbers, basically people doing all kinds of tasks. No need to store all that and all that knowledge. So we basically, they say it's cheaper actually to get away with a smaller brain. So that's an interesting observation. Okay, so that's kind of the history. Let's now look at how they differ. What's the main differentiation? So computers, in the style of John von Neumann and just skip my name right now, Turing. Thank you. Turing basically came up with this idea of the Turing machine, actually, which says that anything can be computed by sequences of instructions read from memory and written into memory. So the concept of the algorithm emerged. Basically, it's a sequence of operations you perform on your data. Now, the way we have computers today, they're still basically executing algorithms. That we program them to do a particular function. And the main optimization function, the optimization metric is you want to do it as fast as possible. Maximize performance while minimizing the energy and the cost while doing so. So that's kind of the main mantra, the main metric we use to design computing. The brain is very different. The brain's function is not to execute algorithm, but it basically is trying to survive. The main goal of what we do is to make sure that our body is healthy and everything goes in the right way. Prosper, make forward in the world, basically go forward in the community. And procreate is make sure we have longevity. It's basically the way that our species keeps on existing. And it's not by optimizing performance, but we are driven by maximizing reward. Where every function we're doing, we're trying to get a reward, and while doing this at the minimum energy. If you can do something, get a reward with less energy, it's a great thing to do. And the way it is governed is shown in this picture. It may be hard to read, but it's basically our whole nervous system is a set of feedback loops. One feedback loop is what we call the inner loop, or this autonomous function. It's the part of our body, of our brain, that makes sure that we're always in the perfect position and condition. It observes temperature, time of day, and so on and so forth. It measures various properties, so it has a bunch of sensors, create patterns, sends those patterns upwards to the brain that combines it with all the information around and help us to basically ultimately make decisions. Should I basically prepare my intestines for food coming down and so on and so forth? Is something going wrong? Do I get a fever? All those type of things are autonomous loop. So small patterns that go upwards, create big picture, and then the big picture is used to make condition or basically make decisions, and then break it down into actions around the body. So that's one loop. The other loop is the outer loop, or basically how we interact with the world. We have 7 senses: smell, hearing, vision, touch, taste, you name it. We have those things, and that's the way we observe the world around us. So these are small patterns, again, that we combine into an understanding of the world, and then translate them into actions, which is motor function. We move, we speak, all of this is how we interact with the world. So that's the basic operation. And all those functions, by the way, are learned. There's no algorithm running there. These are basically functions that you either have genetically there or are learned. So different approaches. This is your digital computer. As I said, this is a Turing-style von Neumann machine where you execute instructions on data, while the brain basically is learning-based. It looks at data, it builds data, uses it, and stores it, and develops into more and more complex patterns, abstractions, and so on and so forth that we then use to make reasonable decisions. So very different in the computational paradigm. Also very different in how computing is mapped. The brain is an event-driven machine. And this is real imaging, actually this is simulated imaging of a brain doing a set of tasks in sequence, like hearing something, interpreting it, and ultimately answering to a question. And what you see is that different parts of the brain, most of the brain, is actually non-active or very little activity most of the time. It's only certain regions that fire up based on events and needs. So it's a very event-driven machine, totally asynchronous. Now look at our computers of today. Extremely synchronous. We have a very complex clocking system that determines when things will happen, and we try to make sure they're all happening at the same time. This takes an enormous amount of effort to build systems like that, because if you think about it, 50 billion transistors that you want to basically all do things in lockstep is not easy, and actually it takes a lot of power. So asynchronous versus very synchronous operation. Now, I claim that both systems are at their limits right now. And the main reason already is that transistors are not going to get smaller anymore, so scaling going forward is getting tougher. And making better brains is not easy either. This is a beautiful article from the Scientific American of about 10 years ago that basically says, what would it take to make a smarter brain? What would you do? Do you make it bigger and have more neurons? Or do you make your neurons faster? Or do you make your neurons smaller so you can pack them more into a certain area? And it turns out that each of those approaches comes with some disadvantages. Making a bigger brain means that you're probably going to need more energy. Means that you're going to have to fight for more food because you have to feed that. So it's also going to be slower. If you look at, for instance, large animals which have huge brains like elephants, the brain is slow actually, and that's why you have more autonomy, because it's hard. Let's see. My screen is still fine. Let's see if we can reset that. Yes. Let me just do. Let me try that again. There's no signal, huh? What? Let me do that. Okay, no. It's coming back? Probably. No, it went to sleep. Let me just do this opposite thing here. Change the ports. Nope. I saw suddenly something blink and it stopped. I've never seen that before. No, there's no signal anymore. Yep. Something. And now this is going to. Yep. Wow. Okay, sorry for that. Let's see if we come back. Okay, so bigger brains, slower, more energy hungry, larger number of neurons, or basically, I would say, well, obviously the bigger brain, smaller neurons is hard to do as well. If you look at a neuron as it operates today, it's really already at the edge of signal-to-noise ratio. The synapses basically work with signals which are just, almost looks like noise. And they're just above, so basically become smaller, noise will become dominant, it won't very well either. So, again, both of our limits, so we have to be innovative to go beyond that. And as I said before, power and energy are the limiting factor in terms of wiring, density of wiring, and so on and so forth. And it's true for the brain. As I already mentioned here, bigger brains take more energy, and you can see actually that the amount of glucose that needs to be consumed is actually a function of the neurons in the brain. So you make bigger brains, you're going to need more food, which might not be the right thing to do. With computers, the same thing. We need somewhere the energy sources, and right now it's batteries, and batteries basically are determining the size of any device you want to play around with. I want to get more computing, I'm going to need more energy or bigger batteries, and that's not something that we're going to solve. So that's kind of setting the tone. Let's look at opportunities, answers. So to me, the answer is really what I call cross-contamination, and it's already happening. Think about it. This is the next generation of robots we're building. If you think about this, this is a combination of a body, a mechanical entity, a physical entity that has a brain somewhere built into it. It basically does the same functions. It needs the same functions as the human body. It needs to basically discover the world around it, interpret it, and take actions. And at the same time, it has to do internal functions to make sure that that body does the right functions and basically survives. So in a sense, we're starting to build similar type structures as, let's say, the human body. On the other side, we're starting to augment our human body with more intelligence around it. And it started, obviously, with things like cell phones, smartphones, where we start carrying part of our memory in our hand. Right? That's what we're doing. All the phone numbers, everything we try to remember, we don't have it anymore in our head, we moved it somewhere else. But if you think about the metaverse, the capability of a human basically living in the cyber world is another example where we now add technology to our biological body. And the good news is that if you start actually looking at the real numbers, we start seeing that brain and chip are becoming somewhat similar. So you take a look at an average brain, is about 1.3 to 1.5 cubic decimeter. It has about 80 billion neurons, 85 billion neurons approximately is a good estimate. Has 100 trillion synapses, which are connections between neurons. And as I already said, 20 watts of average power for about 10,000 teraflops per second. Now, if you look at the most advanced chips that are out there today, this is a chip that was designed by Tesla for their basically learning operation. It's a 7 nanometer CMOS process, not the most advanced one today, but it has 50 billion transistors. It consumes 400 watts and performs 362 teraflops. Now, as you can see, the numbers of devices become similar, even though a neuron is far more complex than a transistor. But it consumes still a lot more power and doesn't have the same computing, but you see that the numbers are on a convergence track. We will see chips pretty soon that will have similar complexity as to what the brain has. There's another form of conversion. As I showed you before, the brain basically works as this event-driven type of mechanism. Very distributed, very parallel. We don't do time sequencing on our brain. We don't try to map multiple functions on the same hardware. Now, the microprocessor was very different. Their transistors were really expensive. The compute part was expensive, so what we did is try to keep it as busy as possible. Time multiplexing, and we need a lot of memory to basically feed it. If you now look at how the next generation or the current generation of chips have evolved, well, first of all, we said, well, we need some more parallelism. We start putting more and more processors on a chip. So we went to 4, quad cores, and so on and so forth. We went to many cores or multi-cores, and today chips have hundreds to thousands of processors in parallel. Not all those processors are running at the same time. So we start doing spatial distribution. We start seeing basically the concept of parallel spatial computation rather than time-based computation. So an important convergence that I can start seeing again between the two. Okay, so convergence is somewhat happening. So let's see what else we can learn from the brain. And to that, I went to there's a very interesting textbook that I advise anybody to read. It's written by Peter Sterling and Simon Laughlin. These are computational neuroscientists. The title of the book is called Principles of Neural Design. And it's like a neuroscience book written by engineers. And very often when you read this type of brain structure book, it's very hard to read for somebody. But this is really written as a way an engineer would look. What are the operational principles? What are the design principles? And what can we learn from them? And just a couple of observations that I think are important and basically will influence the way we're going to do design going forward. I already mentioned the brain is learning-based. Well, rather than is data-driven, rather than basically driven by algorithms. Well, what we see right now is already chips becoming more and more data-driven. Machine learning, artificial intelligence, all those type of things is where we learn from data rather than basically constructing new algorithms. The other important thing about the computation in the brain is that it's statistical. We don't have floating point numbers with 64-bit accuracy anywhere. It's statistical and approximate. It's mostly analog and it's noisy. It is noisy. So we're not trying to be deterministic. Computers today are deterministic devices. You run the same thing, 100 times you should get exactly the same answer. With the brain, it doesn't work that way. It changes. It's overcomplete and redundant. That's also important, because that's why you can lose neurons and still become basically sound coherent and so on. And data is not represented, as already said, by numbers, by patterns, phase relationships, distributions. That's the way we represent data or information. And to me, an important observation is that randomness is a feature, is not something we fight. We should use this to our advantage. Some other ones are, again, already mentioned, that function is mapped to space, not to time. As you can see by your typical brain or neocortex map, where you see that different functions all have been assigned their regions. Okay? So that's mapping to space. There's no such thing as a memory module in our brain. Logic and memory are intertwined. They're sitting together. So intertwinement of memory and logic is important. It's embarrassing, parallel, and sparse. So these are a set of things that we might be able to adopt to generate the next generation of processing. But again, to go back to Peter Sterling's book, here are some of his 5 or 6 different, I would say, observations or design principles. The roadmap to brain-like efficiency. And some of them sound weird. Some of them, obviously, we start understanding quite well. Like the first one, if you look at it, says compute with chemistry as much as possible. I'll come back to that in a second, because that's for an electrical engineer, that sounds kind of weird. Now, the other one makes a lot of sense. Send only information that is needed, and send it as slowly as possible. Now, send it as only the information that's needed. That's not something we do today with our compute systems. We take information from sensors, and then we have a very fast network. We send it to somewhere, a data center, God knows where, do some computation, comes back. Very energy efficient. Why not move the computation closer to where the data is needed? And sending it as slowly as possible. Don't use this gigabit per second networks, but if you can get a slow network, you're going to be more energy efficient. Store new information at the place where it's processed and from where it can be recalled. That means actually that memory should be where the logic, the computing is, not somewhere else, like we have been designing chips for a long time. Complicate. That's the word they use. I changed a little bit to customize. If you know a certain function you want to execute, you could implement this on a general purpose process, but that's going to be inefficient. Why not build a dedicated, customized circuit just for that? You're going to be so much more efficient. Play the number game. Okay, Monte Carlo is good. Basically, randomness is something that can help us to take a bunch of noisy signals together and actually see information arise from it. So it's used very often in the brain. We start seeing it also in computing. And finally, there's a tough one, but it's, again, it's something we need to do if we want to have chips that are basically sustainable, operate for a long period of time. It is self-calibrate, adapt, and heal. Make sure that you're always sitting somewhere in a position that you're basically, if something goes wrong, make sure you can dynamically adapt it. So these are great concepts, I think, and it's worth thinking about each of those and see how they reflect. But the challenge, obviously, for us as computer designers is how to map this into a physical compute platform. I'm just going to go to a couple of them. I don't have the time to go in a lot of details. I'll give you a reference at the end where you can find a lot more. But let's go back a little bit to compute with chemistry. So one thing that our human body is very good at is broadcasting signals. If I basically want to get a particular piece of protein or whatever it is to a part of the body, the way we do it is we inject it into the bloodstream and it travels through the body. And some molecules or some cells will connect to it, other ones will totally ignore it. That's basically communication for free. The blood flow is already happening, so I just write on the blood flow to deliver signals everywhere in the body. This is what McLaughlin calls basically chemical broadcast type of information. It's like he called it wireless almost. And that's interesting. Now, obviously, it's something we don't know how to do very well in our chips. We do this in the wireless world, by the way. Any wireless transceiver you have broadcasts to everybody, and everybody potentially could listen to that. But let me talk a little bit more about the local chemistry operation. Actually, if you look at some of the functions we're performing continuously, right? A synapse is where we basically, the connection between neurons, the way it works is basically electrochemical. You have an electrical signal which travels around the axon, it's a spike. You open up a couple of ion channels, ions travel, and then ion channels open in the receiver and send at the dendrite, and then create electrical signals again. It turns out that that operation is extremely energy efficient. Opening up an ion channel takes about 75 kT. And kT, as I already mentioned, is the absolute minimum, the Landauer limit, or the Shannon limit, as people call it, which is 0.7 kT. Means this works very closely to the absolute minimum we can operate at. If you look at a digital gate, it works orders of magnitude higher levels of energy. 3 orders, 4 orders of magnitude, approximately. So maybe we can try to mimic this. And again, we start seeing some things happening in the world of computing or semiconductor, where we are starting to use some chemistry effects or physical effects to create non-volatile memory. PC RAM, RAM, ferroelectric RAM, these are all examples of where we change the material to store some information for a longer period of time. And it's very cheap. Once you store it there, you can turn off the power, it stays there. So it's a form of chemical computing, chemical local computing. But I just want to point out that all the other approaches, analog computing, mixed signal, as ultimately digital, are taking orders of magnitude more energy. They are faster, which is good, right? So if you really want to go fast, electrical signaling is very good. But if you have time, basically go to things that basically are more energy efficient. And again, with those type of ideas, people now start building this kind of in-memory compute type things, mixed signal processing, analog computing in memory. All those type of ideas are now starting to emerge and have shown orders of magnitude improvement. So it shows that by thinking a little about some of those effects, we actually can make progress. The other one is store information or perform computing where it's needed. So this has led to another concept which is now becoming very much in vogue, is in-sensor computing. Rather than taking sensor data and transmitting it somewhere else, like most sensor networks do, we start putting the intelligence very close to where the sensor is and extract features and limit the amount of information we transmit. Nature is really good at that. If you look at vision, the retina basically does a whole bunch of data extraction because it is a very band-limited channel to the brain. The olfactory system very much so. It has a redundancy of sensors. It extracts some features and then sends this to the cortex, where then you do this in-memory compute type functionality that I was talking about. Massive expansion, random representation, patterns, and so on and so forth. And again, we're learning from that. I'm just going to skip over that, but we now start building structures where memory and logic really starting to get intertwined. All right, so now looking forward. Where does this all lead? This is, again, some speculative type of thinking. Now, one thing I want to observe is that you're not going to end up with a single answer. Depending on where and what you're computing, you will see different answers emerge. A data center with its massive number of processors, which can run in a complete building with cooling and things like that, will probably give another answer than what you see where you interface with the natural world. The natural world, by the way, is slow, right? Nothing happens at gigahertz around us. Most of the things we're trying to observe are hertz or 100 of hertz or something like that. And obviously, so I call it the interaction with the natural world, and they obviously have things in between. So if you look at the numbers or some of the principles, I believe that cloud computing will stay von Neumann for a long period of time to come. So instruction set processing is the right answer for this world. We basically are going to maximize the performance by getting very fast networks that can shuffle terabits of data and have millions of nodes working together. Massive parallelism. On the other side, I believe that when you think about the interaction with the natural world, the IoT, the swarms, there the picture is different. Data rates are kilobits per second. Power levels should be nanowatts, not megawatts or gigawatts. And we will see more and more adoption of those ideas that I was driving around. It's going to be more resembling the brain at that site. And I kind of basically plot this also in this picture where you say there's going to be different answers. And if you want to get your high-performance compute, we still will do these multi-layered structures where we have abstract architectures, traditional compute architectures, lots of them obviously, where we map various abstractions on top of them, like instruction set architectures, processor architectures, and so on and so forth, memory architectures, and then you layer on top of that things like neural nets that can solve real hard problems as we see today in the Googles of the world, the Facebooks of the world, and so on. While on the other side, I believe that you will see computation, or basically physics, the computation itself, and the function getting closer together. In a sense, the physical platform becomes the computation, becomes the function. Very close together, very intertwined, far less overhead, a lot more efficient. So this is, to me, is going to lead to this new generation of compute systems. Systems that are evolutionary. They have to adapt to the task at hand, not basically believing that you know everything about the world. The world changes. You have to adapt to change in the environment. You have to be close to optimally efficient, and inherently they have to be robust and resilient. Because those things are in the environment, you cannot replace them most of the time. They can be there for 50 years, so we have to build this type of structures. And how we'll do that? There's a couple of things that, again, the community is working very hard on. Continuous and fast learning. Not learning somewhere offline, but basically learning that's continuous, looking at the data and adjusting the network as it stands. Robust data representations. Get away from your digital representation, but think about statistical data representation using event-driven. Massively concurrent, and specialized and customized when you can. They will go three-dimensional. This is the next big step we'll see in the brain is a three-dimensional structure. Those devices will be three-dimensional. And as I already mentioned, computing will become physical. We're going to use the physics to perform the computation. And again, there's a number of initiatives. There's an idea of neuromorphic computing, which tries to mimic the brain. A bunch of companies basically providing solutions to that. Still kind of not major in the breakthrough space, but ultimately this thing will happen. I mentioned 3D. This, again, is something that's going to happen. We should be able to build structures soon that resemble this. Actually, by the way, the picture on the left side, you already have it in your pocket. If you think at all the flash memory, all the non-volatile memory you have in your cell phone is built using basically something which is called NAND flash. It's many layers of transistors on top of each other, built around pillars, which basically are the output bit lines, basically. Today, they do 270 layers already. So three-dimensional is possible in very regular structures, but there's some companies already starting to do this also, kind of mimicking brain-like structure, where you have axons going vertically and dendrites going in the other direction. So you start building this kind of brain-like type of taxonomy in those systems as well. And again, I mentioned going to physical computing, gradually going away from this abstract 1-0s to basically physical structures that do matrix multiply in arrays, or basically do interesting statistical combinations like Boltzmann machines, basically by having the transistors directly connected in a network. So physical computing. And I'm going to skip that one. Now, is this going to help us? Are we going to get to brain level complexity soon? This is a good question. So what I did together with a couple of years back with one of my colleagues is, let's see what it takes. If we take a kind of forward-looking perspective, think about 2030 and the technology we have by then. What should we build if we basically take a bunch of neural nets, we stack, or neuromorphic chips, we stack them on top of each other, we cram them as close as possible, how much will we get in terms of computation, computational density, power, and performance? So that was a thought experiment. So if you wanted this chip that basically IBM came out has about 1 million neurons, so you want to have 85 billion neurons, you need 85,000 of those chips. Now we can do very fancy things. We scale them down, they get smaller. We can use fancy packaging and thin them down so we can stack them in 3D format and so on and so forth. You do the best you can. And if you think about something that has the same performance or the same complexity as the brain, turns out that even with those technologies, we're going to be volume-wise about 7 times the size of a human brain. Now, that's pretty good. I actually was impressed. I said, this gets close. The problem still is power. We're still going to be 40 times, power density-wise, 40 times worse than the human brain. But it shows that we're moving forward. Basically, we're approaching to some interesting convergences happening there. All right, to wrap it all up, some more forward conjectures. Just some daydreaming here. What else could be happening? Well, maybe we can learn more from the brain than just the fact that it's a connection of neurons. Actually, if we just look at the layer above it, on some of the functions that are executed, and if we understand some of that, maybe we can use that to change the way we do computation. For instance, SLAM. For those of you who are not familiar with this basically is localization and mapping. Something that every robot has to do, every drone has to do. It has to look around where it is in space and how the space around you looks like, so you can avoid obstacles. Something that is now very often done with neural nets. It's sitting in every automatic car, and any drone has this type of thing. Now, the brain has solved this in a very different way. It has a set of regions which are called play cells in the hippocampus, and has a set of grid cells in the entorhinal cortex. Now, the play cells basically are cells, neurons that fire up if you're in a particular position. And grid cells tell you something about the environment around you. It maps the environment. So this is all mapped into a network of neurons. Now, could we build something similar to that? Rather than building these large neural nets, could we build networks that basically perform exactly that type of functions? Again, that's what some people already try. The other options we can think about is putting intelligence not only in a single device, but like swarms do, distribute the intelligence around and make them work together to perform certain tasks. And again, people are playing around with that. We're still far away from it. But here you see groups of drones interacting with each other, learning from each other, looking around, and doing tasks together. Just in a sense like what swarms do in the real world. Some other options, to me, is, and brings me back to the origin of how I get into this whole space, is why not the symbiosis between physical computing and organic computing? Bring them together. And that's really what brain-machine computers or interfaces really do. And initially, right now, we do this for basically addressing neurodegenerative diseases, for people that have indeed a catastrophic event happening with their nervous system. But you can imagine that this can help us to interact with the brain and basically get information in and out. Again, work that is in its early stages, but you can see many different things. Like, for instance, the example I showed here on the right is a startup company called Kernel that basically uses optical imaging to basically connect with the brain. But here's kind of the further out. Why not build systems that combine neurons and physical transistors? Can I basically build or grow neurons or grow organic neural networks onto chips and make them interact? And the one left side is a project called Brain on a Chip, where indeed they can actually put neurons down, build networks, and differentiate between different neurons. Now, to make it really work, you have to go three-dimensional, as the picture on the right. All right, so in conclusion, I believe there's a lot of things to learn. We basically are in a transition period, and basically opening up our minds, looking around what else is basically around it is in the world around us, in the neuroscience space, the brain, the physical world, and so on and so forth, can help us maybe to think about the next generation of computing. And as I said, if you're interested in this topic, I wrote a lengthy paper. It's about 100 pages. That's going to be published by the end of the year. It's called Of Brains and Computers. So if you're interested, there's a lot more fun information to be found in there. Thank you for your attention.
Thank you, John, for the excellent lecture. Is there any question from the audience? So I have a question. Mm-hmm. We know that the brain and computers are completely two different entities. And I also believe on symbiotic relationship among computers and brains, maybe not humans. How do you expect the technology will evolve in the next years regarding these symbiosis, and how eventually computers and brains can co-evolve from this perspective? Mm-hmm. Don't you believe that could be a natural evolutionary step of humanity?
Mm-hmm. It's a very good question. It's always a dangerous question. But the answer to me is quite obvious. It's already happening. Our brain is already changing through the use of technology. Think about it. Again, I showed the example before. The way we memorize information is already changing dramatically. You're trying to think about something, you go to Wikipedia right away. So already you will see that it's obvious to me that this ultimately will lead to a change in the structure of your brain. You have neurons now that they're used to store things that you're not using anymore. They're redundant. So nature will remove them, or maybe use them for other functions. So, and that's going to continue. I think the fact that now we can change or augment the way we look to the world, right? By putting better interfaces in. And it's going to all start at the periphery. Forget about cognitive and all this type of thing. I have no clue. Nobody knows how it works, so don't even bother. But it's really about eyesight, for instance, hearing, all those type of things. Why not use technology to improve on some of those functions? Hearing, for instance, right now, hearing aids, they work, but they're kind of iffy. Nowadays, at the same time, you see a whole bunch of companies coming up with very, very fancy little ear pods that are quite amazing. They have wireless connectivity, and you start seeing sensors being built into that. The idea of in-ear EEG, where you say, I take your ear and I can put some EEG sensors in there to figure out basically how much stress you have and so on. Use AI to direct where you basically want to pick up sound, beamforming. All those things are happening. Is going to change the way we basically hear, we will see, and so on and so forth. The way we move, all those things are already changing. So I think that is already an evolutionary path around. And it's a slow path. It's not something that's fast. No, not something that jumps on one day, the other day. But yes, absolutely. I believe that in a sense we're going to be augmenting human. Now, what does that mean? Again, it's a very dangerous term, but it's something we already are doing. And I think, and at the same time, and as I said, what we're learning from that brain part, if I look at the evolution of brain-machine interfaces, initially, the way they worked, they had a couple of sensors, and then they had a very simple box that did some Kalman filtering, traditional signal processing. What I see now as a new trend is that people start putting neural nets in that feedback loop. So you actually start a replica of the physical replica of brain computing into the feedback loop. So you start seeing physical and organic brains working together. So that's part of your symbiotic behavior, I believe. So a lot of interesting things already happening. But again, things are slow.
Any other question from audience? Okay, let's do a big applause to Jan. And the link will be available. So please, we have a NAP, a Center for Human-Computer Symbiosis Research through human-computer interaction. So keep tuned and hope to see Jan again next time. Thank you very much.
Thank you.